Hi, everybody. I hope you had a good night and everything's going well. Today, we move into a little bit more with waves, particular resonance and beat frequencies, and a few other things. So, let me just quick remind you where we're at. If you've got two sources of waves at the same frequency, you'll end up with certain points where the waves crest meet crest and trough meets trough. And these are points of constructive interference, where it actually seems louder. There's also places where a wave crest will meet a wave trough, like along this line right here, and you actually get destructive interference, where the waves cancel each other out. And you end up with very minimal amplitudes. And if you happen to be sitting along this point right here and you've got two speakers producing the same tone here, you actually won't hear anything. And there are also, in a lot of theaters, there are dead spots where this happens, where the sound directly from the stage interferes destructively with the sound bouncing off another point in the theater. And so you've got to be careful. Our theater has so many speakers in it that it prevents that kind of problem. But what I want to get into is this idea of beat frequencies, which is different. It happens if you've got two sources of waves at slightly different frequencies. Orchestras actually use the effect of beats. And by the way, Beats not the type of headphone or the brand name of headphones, but Beats in this case is where you end up with two waves getting in phase at certain points, and you end up with constructive areas. Here's a crest meeting crest, you get maximum crest here, and other points where crest meets a trough, and you get destructive interference. But because these are two different frequencies, it goes in and out of phase repeatedly. And so you end up with these kind of bizarre beat frequencies. The amp or the frequency of this amplitude here that just keeps changing is the absolute value of the difference between the two frequencies of the two waves that produced it. You've actually heard this when orchestras are tuning up. If one person just slightly off of the frequency of the other person, you want to hear this wah, 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 wah sound. Or you may have heard it before on a plane, particularly planes that are probably not jets, but more of the prop ones. If the two engines are running at slightly different frequencies, angular velocities, you'll end up with this wah, wah, wah sound. Excuse me for my really crude sound effects. But let me show you really quick what this sounds like. Warning, if you're watching this with headphones, I'm going to ask you to unplug your headphones before we do this next part. Why? There's a slight possibility of seizure if you're wearing these. I love this. There's actually articles about this. So here we've got, I'm going to generate two 500 hertz waves, and if I play them together, you should just hear a nice pure tone. And you're like, okay, but what if I change one of these to 501 hertz? Listen now. You should have heard it get it louder and softer at 1 hertz or 1 time per second. If I make one of these 502, you should have heard 2 oscillations per second. And finally, if I do it at 503, whoops, you should have heard 3 oscillations per second. So you get kind of a feeling for it. And that's what beat frequencies are. They're very easy. Whatever the beat frequency is, it's the difference between the frequencies of the two waves that are interfering with each other. I did that problem already. Sorry, skipping through. And our next step.
Talking about waves, and I wanted to show you this is a wave machine that we keep in the room. Normally this is one of the very fun demos, but I wanted to show it to you anyway. Over on this side, I have a ring stand attached that keeps these rigid so they can't move very well. What I'm going to do is send a pulse along this wave machine, and I want you to see what happens when it runs into that far end. So here it is sending a crest. The crest hits that, comes back as a trough. If I send a trough down, it comes back as a crest. Now what happens if I disconnect the other side? Excuse me. So disconnecting the ring stand from the device. I should walk on the other side of the table. Now this end is free. In other words, it's free to move up and down as well. It's like going from higher density to lower density boundary. Watch what happens this time. So now if I send a crest down, it comes back as a crest. It's not real great reflection, but you can kind of see it. Or if I send a trough down, it comes back as a trough. So again, whenever you run into a boundary where there's greater density, you get a reflection that's inverted. If it runs into a boundary where you run into something that's lower density, in this case it's an open end, you end up bouncing back on the same side. The transmitted pulse, the other media, is always on the same side.
So hopefully you got a feel for that one. I wanted to show you the wave machine because it's just downright cool. But I want to move into standing waves. And a standing wave happens is when a wave runs into a boundary, like you saw up there, it'll reflect back either on the same side if this boundary, this new material here is lower density, or on the opposite side if it's more dense. If you choose the frequency correctly, you'll end up with what looks like a standing wave. And it has to be just the right frequency, but what happens is the wave bounces back, and you end up with this sort of interesting effect where you end up with crest, 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 and there's certain points on this thing which don't move at all. This point right here, this point right here, which I didn't draw very well, this point right here, this point right here, and this point right here. You end up with destructive interference all the time. Those are called nodes. And the points where you get maximum change in or position are called antinodes. And so here we've got an antinode, here we've got an antinode, and here we've got an antinode. Does that make sense? So nodes are minimum points, antinodes maximum displacements, or no motion, maximum motion. So you can get standing waves on various structures. So take a look at this. If you pluck a guitar string, usually the guitar strings are fixed at both ends. The first harmonic, or the fundamental, depending if you're music theory or not, you'll have a node at each end, and the guitar string will just oscillate back and forth here. You can also get it, and I love this with classical guitarists. Classical guitarists will take their pinky finger and put it right here in the middle of the string and then pluck it with their thumb. And by putting their pinky finger right here, it forces a node where there's no oscillations. And that same guitar string, without touching a fret, will now vibrate in the second harmonic mode, where you end up with 3 nodes. And if you check the wavelength here, it's half the wavelength or double the frequency. I can do this on a good day. Most times I can't. If you're a guitar player, you might be able to do this. Classical guitarists do it naturally without even thinking about it. Finally, if you take that same guitar string and put your pinky finger at either the 1/3 or 2/3 of the length and force a node here or here, you can actually force it into this vibration mode. This is the 3rd harmonic. In the reality, whenever you pluck a guitar string, it tends to do a little bit of all of these. Why? Even without trying to put your pinky fingers here, here, or here, you'll end up with a little bit of the other ones, which gives it the richness of tone. It's not just a pure sine wave. You end up with a group of first, second, and third harmonics. The question I have for you is there a mathematical relationship between the harmonics and the wavelength? Well, if you take a look at this, let's define the length of the guitar string as L. And let's take a look at this first one. Well, the length, this entire length, is equal to 1/2 of a wavelength. Remember, one complete wavelength looks like this. This, at any given instant, is only half of it, going from here to here. So the length is equal to 1/2 of a wavelength. So what does that mean the wavelength's equal to? Well, the wavelength of this wave is equal to 2 times L. For the second one here, you'll discover, oh, look, this is exactly one complete oscillation, or one complete wavelength. So that's the wavelength, or wavelength is equal to L. And for the third one, that's 3/2 of the wavelength, or the wavelength is 2/3, just from, for example, from here to here would be one wavelength, 2/3 of that distance L. If I give these some numbers, if I say the first harmonic is n equals 1, the second harmonic's n equals 2, the third harmonic's n equals 3, is there a mathematical relationship that will give us lambda, the wavelength, based on n? And if you look at these equations, you might say, yeah, I can sort of figure it out. Is there a general equation for lambda? And if you think about it, when n equals 1, lambda is 2L. When n equals 2, it's L. When n equals 3, it's 2/3 L. Can you see the pattern? If you haven't seen it yet, it turns out lambda is equal to 2 over n times L, where n is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So you can now tell me, oh, the wavelength, for example, the fifth harmonic would be 2/5 of the length. Yeah, like, okay, I can't, kind of nice. All right, overtones. So how does this relate to, we just talked about the wavelength, how does that relate to the frequency? Well, if you make the wavelength half as big, and remember frequency times wavelength equals velocity, and assuming the velocity inside the string is constant, what happens if you make the wavelength half as big? Well, it's going to double the frequency. And so if the first harmonic's 110 hertz, just choosing an arbitrary frequency, the second one's going to be 220, the next one 330, the next one 440, the next one 550, 660, 770. In physics, we usually call this the first harmonic, second harmonic, third, fourth, fifth, sixth, seventh. If in music theory, oftentimes they call this the fundamental, and then they call this, and don't let this confuse you, the second harmonic is the first overtone, the third harmonic is the second overtone, fourth harmonic is the third. To keep it consistent and to make our n a little bit easier to solve, we'll just keep calling this the first, second, third, fourth, fifth, sixth, and seventh harmonic. But just if you're music theory. I want to show you this just real quick. I told you, like when you pluck a guitar string, you actually end up with multiple frequencies at the same time. We rarely get a musical instrument that produces a pure tone. So in this case, right now I'm producing this beautiful sine wave, produces that. About the only musical instrument that actually produces that is an oboe. In reality, most other instruments start adding some of the other harmonics. This is the second harmonic, third harmonic, fourth harmonic. And when you play this, you'll end up with a slightly more complex, here's all the waves, and here's the constructive interference of all those waves. You end up with something that sounds like this. This is actually more of what like a trumpet sounds like. And it's why a trumpet playing the same note sounds different than, for example, violin playing the same note. A clarinet is even weirder. Clarinets tend to do a lot of the odd ones with very little of the fundamentals, the second and the fourth. And so, for example, a clarinet playing that same note will probably sound something like this. The wavelength looks a little different. Why? It's got different amounts of the different harmonics. I guess I should put in here. If I put back the fundamental, you can sort of hear it. This is more of what a clarinet sounds like. The harmonics look something like that. All right. Switching back over here again. So this is a mechanical wave generator. If you can see, this device over here is oscillating up and down. This little pole moves up and down at whatever rate I have this set. Right now I've got it set at 1 hertz. If I increase that frequency a little bit, let's say up to 5 hertz, you'll see that this thing is now oscillating 5 times per second, and it's generating a wave down this elastic string. Now the wave isn't doing much right now. Oh, I should show you what's on the other end of the elastic string. It just goes over this pulley and then down to this hanging mass, which is just hanging there just to provide some constant tension. So the wave moves down at some constant velocity down this string, runs into the pulley at the far end, which acts like a more dense point, and gets inverted as it reflects back, and then comes back here, gets inverted again. But you'll discover that, and I'm going to increase the frequency. This is 6 hertz, 7 hertz, 8 hertz. You don't get anything really interesting going on until I get to, here I go, 9, and now 10 hertz. Do you see what just suddenly happened? We got resonance. In other words, the reflected wave coming back is adding to the wave that's coming in, and this is what's called a standing wave. And if you think about it, this is 1/2 of a complete wave. This is half of a wavelength, if you suddenly did a little snapshot of it at any given instant. And it's only certain frequencies that'll set up standing waves.
So right now we're at 10 hertz, if you can sort of see where I'm at down here. And now I'm going to increase it again, and I want to show you what happens. Here's 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. And notice what just happened. At 20, I got another standing wave. And I guess I should aim it from straight across here so you can see that it's equally spaced. It's not oscillating in two halves. And if you did a freeze frame of it, it would be one complete oscillation. So right now, the wavelength between ear and ear is exactly one wavelength. And yeah, if I gave you the distance on the table between those 2 points, you actually could calculate the wavelength of this wave. You know the frequency, it's 10 hertz, and you could actually calculate the velocity of the wave in this string. All right, you may have guessed now, it should be possible to get 3 of these antinodes in here at the same time. 10 hertz for the first one, 20 hertz for the second one. You might guess, and you're absolutely right, if I take the signal generator up to 30 hertz, notice what's happening. Oh no, the video is actually freaking. If you don't know video, it's actually being shot at 60 frames per second, and because of that, it's actually kind of frozen this in place. In reality, this is not frozen, it's oscillating at all 3 points, but it's formed a standing wave. Let me take it up to 40 hertz so I can avoid the problem. And at 40 hertz, if you can see this, it's again formed a standing wave where in this case it is exactly 2 wavelengths from one point to another. And I can continue to do this. If I take it to 50 hertz, I would end up with 5 antinodes, or places of maximum oscillation. But there's one thing I want to show you real quick, and this time not a camera oscillation. Excuse me for a second, I'm going to run over and turn off the lights. Look, you get a tour of the classroom. Dun, 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 dun. And taking it back here, I set up a strobe light. And for those of you who don't know, strobe lights, they're kind of fun. You can make them flash at any given rate. Right now it's flashing at 1 hertz. But I want to show you what happens here if I get it going close to 40 hertz, which is what that oscillation is. Hopefully my camera doesn't freak out too badly. Hold tight. It is freaking out a bit. I hope this works. So there it is. At 40 hertz now, this is flashing, the strobe light's flashing once or 40 times per second, and this is oscillating 40 times per second, and I can actually stop the wave in midair. If I change the frequency of the strobe light slightly, you can actually see the oscillation because I'm catching it. I'm actually not stopping it. It's just because of the strobe effect, I can make it appear to almost stop and go again. Just real quick, let me show you what 50 hertz does. At 50 hertz, taking it back up again. And sure enough, we get 5 antinodes in this. Let me turn off the strobe light so you can see a little bit better. 1, 2, 3, 4, and 5. And yes, 60 hertz would produce 6 antinodes, 70 hertz, 7 antinodes, and you get the whole idea. Great.
Cool. So hopefully you enjoyed that part. I want to talk, so you just saw strings, and we're pretty comfortable with strings, but you can also have musical instruments that are closed at one end and open at the other. For example, a flute is actually open at one end and closed at the other. You blow in the little mouthpiece on one side there. There's other musical instruments that are similar to that as well. And what happens here is you'll end up with an antinode near the open end. This is considered an open end over here. And the closed end, you end up with a node. Besides flutes, I should mention like organ pipes. Some of them are open or closed at one end, some are open at both. But you end up producing different harmonics depending on how it happens. So in this organ pipe, you end up with an antinode here and a node here, like it's shown over here. And then this one, antinode, node, antinode, node. And here, antinode, node, antinode, node, antinode, node. If we number these again in terms of first harmonic, n equals 1, second harmonic, n equals 2, third harmonic, n equals 3. And if you look at, I need to change my pen color here real quick, not white, blue, and take a look at these relationships right here. can you figure out the mathematical relationship for this one? Where if you plugged in n, you would get these. And this one, by the way, I get students who immediately see it, and other people like, what? I don't see a pattern. It's a little bit more complex than the other one. If you're not ready for it, well, here it comes in 3, 2, 1, boom. In this case, the wavelength is equal to 4, notice it's 4 on top in each case, over 2n minus 1 times L, where n is 1, 2, 3, 4, 5, 6, 7, 8. And so this equation is definitely more complex than the other ones. But this is for oscillations open at one end, closed at the other. So yeah, you should also, of course, ask then what happens if they're open at both ends. So in an organ pipe, you have a little baffle here, open here, and open here. You'll end up with antinodes at both ends. What happens there? Well, now you end up with this relationship. In the first harmonic, lambda is equal to 2L. In the second one, L equals 2. And this one, 2/3 of L. Whoops, I kind of drew through that. And if we again define this as n equals 1, n equals 2, n equals 3 for the first, second, and third harmonic, what's the relationship? In this case, you can sort of see it. It's elegant, it's beautiful. It's the same equation we actually had for strings. Except in strings, you end up with nodes at both ends. Here you end up with antinodes at both ends. But the relationship is still the same. Resonance, our last topic I want to move into, is an increase in amplitude of an oscillation or mechanical system exposed to periodic force whose frequencies equal or very close to the natural or undamped frequency of the system. And you're saying, what? Yeah, let me tell you real quick about Ella Fitzgerald, one of my favorite jazz singers. She had a phenomenal acoustic memory. One of her stunts she used to do repeatedly would be to do an entire bebop jazz session, and then the very last note of the evening would be the exact frequency of a wine glass that she placed in front of one of the speakers on stage. Now, wine glasses don't have a pure tone. They have some quarter note tone. Before she hit the concert, she'd hit it with her finger, bing, and remember that exact tone. And after doing her entire concert, her last note would be that ding. Sorry, that was really bad. The note on that particular one. And let me show you a recording which became a Memorex commercial.
Ella Fitzgerald. She's attempting to shatter a glass with her amplified voice. She did it. You are now hearing the Memorex cassette tape recording we just made of Ella. Now you'll see a glass shatter again. But is it Ella or is it Memorex?
I'll never tell.
Now, hear new Memorex. We've added MRX2 oxide.
Sorry, couldn't resist that one. Yes, I realize it's ancient. Oh, it's got another one. I don't want to show you that one. All right, moving on. It also happens with larger objects. In this case, this is the Tacoma Narrows Bridge in Washington State. And this is steel and concrete. This is not rubber. This is steel suspension bridge. And it turns out, as wind blew over it, the wind actually produced a certain frequency across the roadbed. And on this particular date, the wind was fairly constant, and the tone, I'll call it a tone, or the frequency produced by the wind blowing over the bridge, was equal to the natural or resonant frequency of the bridge itself. What happened? Its oscillations became larger and larger and larger until you saw it doing this. And yes, it eventually then actually destroyed the bridge itself. You'll see that in just a moment. Sorry, this is also old video. 1940s? No, 40s, 50s. I can't remember the exact date this happened. Up to this point, bridge designers never thought that resonance could play a major role in bridge design or architectural design. But after this disaster, I mean, it wasn't a disaster, there's only one fatality. The dog who was in the car, there's a story behind that one. The professor who's standing here on the bridge right here is trying to get his dog to come out of the back seat of the car but he won't. He's laying on the floor whimpering. He tried pulling him out, but he couldn't do it, and he's still trying to call to the dog to walk out. But in this case, the wind blowing crossing, you can sort of see it here, caused that. Here's the car is still sitting here with the rear door open. Here's the professor calling to his dog. There's actually got a little note in here about that. Trying to get the dog out of the car. I forgot how long this was. But this is regular asphalt, steel girders, steel cables, not rubber, and it's oscillating uncontrollably. I'm waiting for the road bread to break up. After this disaster, all architectural models, especially bridges, go through wind tunnel tests. And also, skyscraper designs go through vibrational checks as well. And you might say, well, why is that? Well, for example, the new Shanghai Tower here in Shanghai, they were worried about wind between it and the other building causing the Shanghai Tower to begin to resonate at a certain frequency. If that happened, it could actually destroy the building. The other part we have to be concerned about is resonance due to earthquake waves. Earthquake waves are generally in the range of 3 to 10 hertz oscillations per second. If a building oscillates or has its natural frequency in that range, it can easily start oscillating or resonating during an earthquake and get destroyed. Unfortunately, Concordia oscillates at about 3 hertz, so we're right at that lower end. But here's the bridge collapse. And it literally just came apart. It lasted for months. People used to drive across it on windy days, and it would just do mildly oscillations, mild ones. In this case, though, the wind was going at just the right speed to produce a frequency that was exactly equal to the resonant frequency of that center span, and that's what destroyed it. With great knowledge comes great responsibility. I just told you that this building oscillates, or Concordia resonates at 3 hertz. Yes, you could actually make it resonate. If you got yourself and 2 of your friends and you each jumped once per second, a third of the second apart, you could actually get this floor, or the floors in the science wing, to start oscillating larger and larger frequencies. I wouldn't recommend it. If you did actually hit resonance, besides the building oscillating, it could literally come apart. Not a great idea. All right. I'm going to move outside of that. There's one other piece in this chapter on Doppler effect. It's worthy to read about a little bit. Don't worry about too much of it. The idea is that if something's traveling towards you, the wavelength gets shorter and you'll hear a higher frequency. If an object sound source is moving away from you, you'll hear a longer wavelength or a lower frequency. The same thing's true if the listener is in motion. And I just need you to understand it qualitatively. But you can look at the formula as you'd like inside of the chapter as well. I want to do 2 textbook problems from tonight just so you can sort of see it. In the first one, number 35, this is one that always students struggle with. When the boat is at this position right here, the radio signal from these 2 antennas is very strong. Because why? Because it's equal distance away from both. But when it's at point D right here, it gets a minimum signal. The sound sources from these 2 operating at the same frequency produce destructive interference at this point. And the question is, determine the wavelength of the radio waves. It's just a question of distance. At this point right here, you're 600 meters away from this antenna, and using just a little bit of Pythagorean theorem, you're 1,000 meters away from this one. What does that mean? When you're at this point right here, the waves must be out of phase. Crest meets a trough. So the distance between the 2 antennas must be different by a factor of 1/2 of the wavelength. So it ends up out of phase. Therefore, 1/2 the wavelength is equal to the distance difference in these 2 distances, or 400 meters. Therefore, the wavelength must be 800 meters of this radio wave. Hopefully that makes sense. The other one I want to do for you is number 52. A tunnel underneath the river is 2 kilometers long. At what frequencies in the air does the tunnel resonate? Explain whether it be good to make the rule against blowing your car horn while you're in the tunnel. Well, the tunnel is open at both ends, so we end up with resonance or standing waves in it that look like this. And if you remember, the formula for that was just this. So what wavelengths would resonate if this length is 2,000 meters? If you plug it into this formula down here, you'll discover lambda is 4,000, 2,000, 1330, what's the next one in the pattern? 1,000 meters, et cetera, et cetera. Just keep adding them up and they get shorter. Assuming the speed of sound is 300 meters or 340 meters per second, I think at the beginning of the questions in your book, it tells you to assume that for sound. And using our wave equation, frequency times wavelength equals velocity, our resonant frequencies would be 0.85 hertz, 0.17 hertz, 0.26 hertz. Something's wrong with that. One of these is wrong. You're just plugging in this in for the wavelength and calculating frequency. This should be a regular pattern. I did one of these wrong. So the question then for part B, would it be good to advise people against blowing your car horn? The answer is it probably won't resonate. Car horns are usually about 400 hertz, 1,000 hertz in that range. It probably won't resonate. However, it is annoying. So maybe you want to make the rule just for the annoying factor, but it probably won't resonate. With that, I hope you have a wonderful night. Send me questions. We're wrapping up the chapter and moving into review for next time. Talk to you soon. Bye.